Thank you so much for the introduction, Dr. Castillo. So yes, this talk is going to be a high-level overview of some of the research projects that I worked on. So I meant for this talk to be very accessible to students. So it's going to be high level. I do not show many details, but please, if you have any questions, ask, okay? So here's some information, just basic information about me and my website if you want to check a little bit about my research more in detail. So you can find publications, presentations, all on my website. So this is the overview of my talk. So going chronological order, some of the research project that I worked on. So starting from my PhD, and then postdoc, and then the position that I had after my postdoc, which is a research software engineer position. You guys can all hear me okay? Okay, and hopefully on Zoom they can also hear me okay? So, but before diving in, I just want to tell you a little bit about myself, where I grew up. I grew up in Siena, Tuscany, Italy. This is a beautiful picture of our town center, our historic town center. A lot of people ask me why I left when I talk about where I'm from. So I hold a Bachelor of Science and Master of Science in Mathematical Sciences from the University of Siena, and then, as Dr. Castillo introduced, the PhD program in Applied Math at NJIT, postdoc at University of Colorado Boulder, also called CU Boulder, and then I was a research software engineer for over 3 years at Caltech in the CLIMA project. So my PhD research focused on non-Newtonian fluids. In particular, viscoelastic fluids that represent polymeric fluids. So viscoelastic fluids are really ubiquitous and can be found anywhere around us. For instance, all of our bodily fluids are actually viscoelastic fluids. So it could be a little gross, but if you think about mucus and saliva and blood, those are all viscoelastic fluids. Or for instance, we can find them anywhere in the kitchen or in our bathroom, like shampoo, toothpaste, or ketchup. These are all fluids that behave viscoelastically, and I'm going to tell you in a second what that means. For applications of interest, for instance, biomedical applications, for diagnostic testing, there is, for instance, some viscoelastic polymeric fluids that is deposited on a substrate, like when you do like in vitro analysis, and or for instance, some engineering applications, inkjet printing is an example of the type of study, numerical studies that I was conducting in my PhD research. Because for instance, in inkjet printing, you can see that you have a very, very tiny droplets that this deposit nanoscale, nanometer scale films on a solid substrate. So viscoelastic materials behave a little bit unintuitively relative to other more common fluids that we find in our everyday life, like water, which is inviscid, or honey, which is viscous fluid. They are characterized by these three main material properties. So they do show hysteresis, which means a loop in the stress-strain rate curve. They do show stress relaxation, which means for constant strain, you have decreasing stress. This is actually a very nice property of materials, which we also experience in our body when we do some physical stretching. So you exert some constant strain on your muscle, you have some constant displacement, eventually your muscle starts to relax. So that's a decrease in stress. And then creep, which is the opposite. For constant stress, you have increasing strain. So the materials, they can be described via mechanical system analogs. So for instance, here on the top, we see the Hookean law for linear elastic solids. Like most of us are familiar with this law, where the stress tensor is linearly dependent on the strain with the multiplicity constant, which is just the shear elastic modulus. And this is characterized by the schematic of a spring. A spring is an energy storing device. Also, we can think of Newtonian fluids, where the constitutive relationship is just a linear relationship again, where now we see the parallel, we see how similar it is. So if you compare the two rows, we just have on the right-hand side, we have the strain rate, because in fluids, as opposed to solid mechanics, we analyze the strain rate. So we have how fast the strain changes. And the relationship is still linear in the viscous case, Newtonian case. So we have stress tensor equal to 2 eta strain rate, where eta is the shear dynamic viscosity. And this is represented by a dashpot, which is an energy dissipating device. If you pair the two in parallel, you have what is called the Kelvin-Voigt material, which is suitable to describe linear viscoelastic models. If you pair the two in series, you have the Maxwell model. And this is the simplest non-Newtonian fluid that you can represent. It's a linear viscoelastic fluid. And we see that the constitutive relationship has time derivative of the stress tensor on the left-hand side. And there is also a lambda one that appears here, which is called relaxation time. This is a characteristic time of this elastic, viscoelastic material, defined as the ratio between eta over g. So here we see how we can build complexity of this constitutive relationship by adding more devices, either in series or in parallel. So the next step in complexity is the constitutive model that I analyzed in my PhD work, which is constructed by adding the Maxwell system. So we have a dashpot and a spring in series with another dashpot in parallel. So now we have two dashpots, we have two different viscosity, because you have to think that these are polymeric fluids. Usually they are constituted as a solution. So you have a polymeric solute and a viscosity solvent. So you have the Newtonian part of the solvent plus the polymeric non-Newtonian solute. So this is characterized by two time constants. And we have, you see that it's a non-Newtonian fluid or characteristic equation, because we see we have time derivative of the stress tensor on the left-hand side. And it's also very peculiar because we end up having time derivative of the strain rate on the right-hand side. So we have the second time derivative of the strain. So these are the classical equations to describe conservation of incompressible fluids. So the first one is just the conservation of linear momentum. And the second one is just the continuity equation, so conservation of mass or incompressibility in this case. The first one, we add some body forces. So we have an extra source term. And also you can see the divergence of stress tensor, and you can see negative gradient of pressure, where we define P, just the usual pressure, and then plus capital pi, which is an additional disjoining pressure due to the van der Waals interaction, attraction, repulsion force. So because we're trying to describe fluids at a very, in a very confined space, these attraction repulsion force are actually important because they describe the attraction of the fluid molecules towards the solid substrate molecules. I'm going to show you the setup in a second. So this is the typical setup of thin films approximations, also called long wave approximations, where the length scale is much, much larger than the height scale. So remember that, for instance, the inkjet printing application, we have a very, very thin, like nanometer scale layer deposited on the substrate. So these are all the boundary conditions. And by doing the magic, which is non-dimensionalization analysis, you're using scalings, you can approximate the solution H of X and T, so at a given point in space and time. So in this case, by doing non-dimensionalization, we go from two equations in two unknowns, like the Navier-Stokes equations. We go to one equation in one unknown for H. So we track the interface function. Now, you can look at this for a second and think, oh, wow, this is a beast of an equation to solve. Yes. So what was the advantage? Well, the advantage is that we went from two equations in two unknown, in one equation in one unknown. The way I factorize this, we also have some capital Q and capital R that satisfies two linear ODEs, but they can be solved exactly and plugged back into the equation. So this is really one giant equation. We can look at this for a second and see that this is a second order in time equation. We have mixed space and time derivatives. And typical of all thin films or long waves approximation, we have the fourth order in space derivative. Because here I have the third order plus the fourth order up here. This is really due to surface tension. In this type of problem, surface tension matters. We cannot disregard this term, okay? So these types of problems at this scale, surface tension matters. So some examples of this evolution. So we start with perturbing a surface, and we see how this evolves in time. In some of the settings that I analyzed, it is called de-wetting. So you want to see, starting with the perturbation of your surface, you want to see how the fluid de-wets, which means separates into separate blobs. However, the separation for this formulation, since the function has to be continuous, you still have even when it separates into separate blobs, you still have some very, very tiny layer deposited at the substrate that is called equilibrium or precursor thickness. And it stays there, and it's due to the van der Waals force that I was mentioning earlier. So this is an evolution in time. So this surface is just perturbed and it separates into different blobs or patches of fluid. What was novel in my research, not only conducting such simulations with all of these terms, because we also included slippage with the substrate as an extra term that was never solved for before, but I was able to show that we had the presence of these satellite droplets here due to viscoelasticity. And these satellite droplets are also found in experimental settings. They're sometimes in an extensional flow. They're called beads on a string. Yes.
The vorticity of this model?
Vorticity, no.
Oh, okay.
No.
Okay.
Yes.
So can you explain what's being perturbed here? You have a surface.
Yeah, so you start with a surface, you start with a flat surface and give it, like, let's say, a sinusoidal perturbation. And then you see how this evolves in time. So you solve for the full nonlinear equation, which is this one that I showed.
You're graphing something about the fluid layer, right?
Yes, so the height. We're solving for the height here, the function. We're tracking the height in space and time. So
is this the height relative to the surface?
Yes.
That forms a boundary condition.
It is the interface of the fluid. So here, this is an interfacial flow. We're solving for the interface of the fluid. Okay. There is boundary condition at the interface, which is the kinematic boundary condition, this one, that tells us that the function itself moves with the velocity of the flow.
Right, but I'm trying to understand, like in the graph, what's being represented on the next slide.
So
I mean,
why
you're perturbing the interface?
Yes.
And you're looking at what happens to a thin film at that interface.
The thin film described by that interface. Yeah, the interface between the fluid and the surrounding air. So this, for instance, This is a two-phase flow because here we have fluid 1, which is the liquid, and fluid 2, which is the air.
Which is like gas. Okay.
The surrounding ambient air, yes.
Wait. There is in the chat, there was a
There's a
question
question in the
before.
chat.
Yeah.
It says, can the mechanical analogs involve nonlinear couplings? And if yes, what would be the implications in your analysis?
Nonlinear coupling as in what sense? Like these are already nonlinear equations. And so I don't know, I hope they can hear me. These are already nonlinear relationship constitutive models, because here you can see that there is time derivative of the stress tensor, which makes it nonlinear. However, it is a linear ODE for the stress tensor. There are also constitutive models that consider different derivatives of the stress tensor. And for instance, one such model is called the Aldroyd-B model, which we did not consider in this work. So I hope that answers the question.
He said he can post this question on the microphone.
Yeah. No. This
Oh, okay.
okay for later. But also they can see you and they can hear you very well.
Okay. So a second part of my PhD, and just to let you know, the numerics for this first part was very simple. We just used staggered break finite differences scheme, second order, and just very simple naive numerics because the equation to solve was already complicated enough. We didn't want to go like too fancy with the numerics. A second part of my PhD thesis analyzed instead viscoelastic membranes. For this part, I use linear finite element stress under plane stress formulation. And in here, I also, again, compare different constitutive models. So I played around a little bit with linear elasticity or linear viscoelasticity due to Maxwell model. So you can think of this like a shear problem on the left panel and an extensional problem on the right panel. You can think of this as being gel-like materials described by the Maxwell model. So some gel-like soft matter type of membrane, okay, being sheared or elongated. Yes.
How big are the membranes? Like a meter or?
No, here we're talking about like centimeters, like 10 centimeters by 1, for instance, is this example. So this line of research led to these publications for me in my PhD, 3 first other publications. And also a couple of years after finishing my PhD, a student from University of Edinburgh contacted me and he wanted to collaborate with me. So I ended up co-supervising his PhD work. So here is Bamihole, his the student work who ended up publishing his work. A side project that I had in my PhD is when I did my research internship at Pixar Animation. So especially for students, some of them might be interested in learning about, internship experience during PhD. I really did enjoy my internship experience, and I worked at Pixar with developing 2 proprietary libraries in C++ for viscous animations of fluids on curved surfaces, including fluid-solid interactions. So here are some examples. In this project in particular, we use discrete exterior calculus, DEC, on arbitrary polygons. So that's defined on arbitrary polygonal meshes. In this case, we use a vorticity formulation of the 2D Navier-Stokes equation. And you can see example here on the left. For instance, this is flow on the sphere with a solid obstacle. So in this particular case, it was interesting because we allowed the user to select the solid obstacles real time. So the user could click on the edges of the elements that they wanted to construct a boundary. And in real time, we were doing the simulation. On the right-hand side here, you see an example of a polygonal mesh, a mixed mesh. Here we have hexagons, pentagons, we have several different types of elements. And we see an example of a flow on a polygonal mesh. Okay, yes.
Did Pixar allow you to publish in transactions on graphics?
I wish I did have so much result in a 12-week internship, but of course it was enough to complete 2 projects there, but not enough to have something like in a publishable state. But if, there were people who were staying longer, maybe they were staying for 1 year. In that case, they called that residency program. So if you stay for a residency program, then good chances you have to publish with them. Here I had fun in running my code on different shapes, like here on the left, you can think of this as a chocolate truffle, and here on the right as a glazed donut, where the fluid, in this case, it's a thin film, so similar to my PhD research, but on flowing on curved surfaces. Okay, any questions up to this point? Okay, yeah?
Do you still have access to Houdini, or did they just give you a 3-month access?
Yeah, I had access out when I was working there, but Houdini have some free versions, I think. They do. So on to my postdoc project, I joined, yes, please. Yeah, so I can share some details. I did not post the details here, but I can definitely can share some details on discrete exterior calculus. It's actually pretty neat for this type of problems. Yes.
I think it knows the relation of exterior derivative, right?
It has relation with what? Sorry?
The notions of an exterior derivative, right?
Yes, and
It's from different performance things.
yes. So yeah, very nice. So on to my postdoc project. I joined the Department of Computer Science at University of Colorado Boulder under the supervision of Jed Brown. This was a very large collaborative project. I had to move faster, I realized, but this was a very large collaborative project that involved several institutions and national labs under the umbrella of the exascale computing project. So I don't know if you're familiar with the exascale computing project, but sometime like 2016, I think under the Obama administration, there was this big push towards exascale computing. So the goal was to reach exascale computing, which is 10 to the 18 floating point operations per second. However, not only building big machines is enough to have that type of computing, but you also have to exploit those machines at best. You want to have fast algorithms and efficient algorithms for your computation. So our project involved efficient operator evaluation. So we built a mathematical software library for high order discretizations, in particular spectral element operators that would be efficient on heterogeneous architecture. So heterogeneous meaning including GPUs and CPUs, which are the modern type of architecture. So here is the motivation slide on why high order spectral element. So for decades, high order methods have been considered too computationally expensive because they rely on sparse matrix representation. And sparse matrix assembly costs OP to the D storage and OP to the 2D compute per degree of freedom, so compute per DOF in D dimension. So this, of course, is very expensive for basis polynomial order P that you can choose to be as high as you want. On the other hand, optimized code, which does not assemble the sparse matrix, which is called matrix-free representation, it can achieve order 1 storage and order P compute per degree of freedom. So these are very efficient. And these two graphs, they show you two different metrics for performance. The right-hand side panel here, it shows a graph of flops per DOF, so floating point operations per degree of freedom over polynomial order. And here we're comparing assembling a matrix versus non-assembling a matrix. And in the non-assembled version, which is this 4, we also have a different representation where we can take advantage of some storage. So here we see, and this is theoretical performance model. This is not actual experiment. Theoretical, we can see that assembling a matrix does never make sense, because here we can see that the cost skyrockets with the polynomial order increase. And also, this is a model of performance that does not really make sense nowadays. It was relevant up to a couple of decades ago when processors were limited by clock speed, but that's not the case anymore. Nowadays, we worry about memory bandwidth, which is what is the bottleneck for high performance computing. So nowadays, we worry about the left graph. The left graph shows bytes per degrees of freedom, so memory bandwidth over polynomial order. And here we see that, again, assembling a matrix does never make sense. The cost skyrockets. And instead, for high-order method, matrix-free representation, the cost goes down with the order. So in here, we see that the higher the order, the more efficient the representation is. So this is in favor of using high-order methods. Like, why not use them if they are the most efficient? They give you the best accuracy and order and rate of convergence by definition. So libseed is a library that can define these high-order spectral operators on any architecture because it's really an algebraic library. So it does not need to know anything about the geometry of your problem. It just needs to know about what order of element you want to choose, and you can select that at runtime. Order of discretization you want to use. you can select that at runtime. Resolution, you can select that at runtime. And if you want to run on a CPU or a GPU, you can select that at runtime as well. So libc can be seen as being like a low-level library as opposed to other higher level libraries like known in the finite element community like MFM or PEXI or NEXT 5000, which is used by CFD community. And they can provide the parallelization for libc. Then libc dispatches on different backends that are optimized for different architectures, like CPU, NVIDIA GPU, or AMD GPU. So there is performance portability, yes.
Is Magma the computer algebra system?
Magma is one of the backends used for dense small matrix computations.
Okay, but it's the computer algebra open source system
Yes.
that has dense
Yes.
matrices.
Yes.
things like
Yes,
that.
developed by UTK. Yeah. Okay. Very quickly, I don't want to bother you with some performance graphs because these are also outdated now, but here we reached gigaflops in some of our benchmarks. This was really also the foundation for application examples. So usually in HPC community, a lot of people show performance benchmarks, but they show them on the simplest example, like the simplest elliptic equation, like Laplace problem. So when you show those benchmarks on the simplest, best behaved equation, you're not really using it on a challenging problem. So we use this on challenging problems in computational fluid dynamics or solid mechanics. So here you see a compression of this Schwartz periodic minimal surface. This could be used in additive manufacturing and robotics. And we use this in some direct numerical simulations of a flat plate. For instance, here you see some turbulence here in the bottom layer. These are the students that I helped co-supervise while I was a postdoc at CU Boulder. And yes, I would like to acknowledge their work as well. Questions here? I can move on to the next part and final part. Okay. So this is CLIMA. CLIMA is a coalition of scientists, engineers, applied mathematicians like me from Caltech, MIT, and NASA JPL. So I was part of this project, which stands for Climate Modeling Alliance, for a little over 3 years. They are building the first Earth system model in the Julia dynamic programming language. This is the very first effort to build an Earth system model, so a climate model that describes the entire Earth climate in the Julia language. So historically, a lot of climate models have been written, at least in the US, by national labs, which has created a lot of legacy code that stems from like the 70s, the 80s efforts. And nowadays, a lot of this legacy code, they're really struggling to hire people, to find people who want to work on those codes. Like students nowadays, they're not really that interested in Fortran. So building an entire climate model from scratch in Julia, it was also a decision to attract a lot of young talent. And you can see how this research group has a lot of young faces, really a lot of students, yes.
Can you, will the Fortran climate code still eat Julia for
Well,
lunch?
we'll see, because we're now about to deploy this model. So we will have like actual comparison, like in terms of performance and in terms of different metrics that you want to have.
What's the difference between the Fortran version and the Julia?
Well, I'm going to show you a little bit about the user interface. So you're going to see how user-friendly this is in Julia. So that is one pro. And another pro is reproducibility and package maintenance in Julia, which is optimal right now. So Julia really solved a lot of problems. And also in this case, it is also solved what they call the two-language problem. But I don't want to go into much details. What is an Earth system model? So for students who might have not encountered this application in Earth sciences, it's a system that describes our entire Earth. So our entire Earth as a physical system is a multi-scale, multi-physics problem It describes several different physical processes. For instance, in this schematic here on the left panel, we can see how the Earth could be divided into the atmosphere, the ocean component, the land biosphere, which connects lands to the atmosphere, the ocean biospheres, which connects the ocean to the atmosphere. For instance, sea ice and land ice are other models. All of these models historically have been developed by different groups, even in different languages. And then people who wanted to couple everything into a climate model, they had to solve different language problems, different import and exports of different file formats. But by doing this in a unified group, of course, allows for easier coupling. What Klima also wants to innovate with is not just the language. That would not be enough of an innovation. They want to use, take advantage of data simulation, machine learning, and AI techniques to incorporate some information to couple very high resolution simulation on a regional scale. So if you think of a large eddy simulation that can be run on a computational block, which is just like a rectangular block, then you can feed that to the global scale circulation model, so the GCM model, which is the global model. Because otherwise, you cannot really achieve the very high resolution on a global scale. Yes.
How do you reinitialize it?
I'm sorry?
How do you reinitialize the model with
so
data from?
by using parameterization, and of course, this parameterization are here. What I hear is like they use parameterization to inform the global circulation model. So I don't know if that.
Well,
Like,
do you
question.
use all the data from airplanes coming?
The data can come from a plethora of sources. It could be observations like satellite observations, or it could be also historical data if you're doing like reanalysis, what they call it, reanalysis. Okay, that's it. Just one. Can I go? Okay, so in this project, I participated on what they call the dynamical core, the DICORE, which is again a numerical library that defines how you discretize your equations, so how you solve the system, the PDEs. We are focusing on support for both CPUs and GPUs using the same single source code. So you do not have to write another code to run on a GPU. You only have one single source code. Julia has an interactive REPL, which uses just-in-time compilation. You can write generic code, and the compiler will specialize at runtime on the different type of arguments. This is similar to polymorphism in other languages like C++, but Julia does it this way. Julia is accessible and extensible by a mixture of users. So by having a very nice user-friendly interface, we could have an entry-level contributions by, let's say, students or anyone who wanted to approach the. Yes.
How do you put this thing onto the M4 and M5 chip from Apple?
I'm sorry, M4.
The M4 and M5 chips at Apple computers.
You can run this on Apple's. Yeah.
Yeah, but also you need to let her continue.
So, the main contribution for me was in a package in this ecosystem, which is called ClimaCore, which again stands for the dynamical core, which is how you discretize all of these equations. In this particular package, we use spectral element methods in the horizontal dimension and staggered finite differences in the vertical direction. And this is because the atmosphere is a very thin shell. So processes that happen in the vertical have a much different scale than processes that happen in the horizontal, okay? So we only have, 45 kilometers high atmosphere as opposed to what's the radius of the Earth. This package in particular, though, has support for both continuous and discontinuous Galerkin, and also both spherical and Cartesian grids. So some of my main contributions have been in grid generation, for instance, different cube spheres. So the cube sphere is what is the main grid of use in earth sciences. There are different types, equiangular, equidistant, or conformal. They have different properties. For instance, one can exacerbate the CFL condition, so you want to be careful about this, especially towards the corners of the cube sphere. Added high-order differential operators and flux limiters in the vertical dimension, a lot of unit testing and best practices like tutorials, documentation, and whatnot. So here's an example of why a student nowadays might want to choose this to solve problems rather than Fortran. Here's how the interface looks like. In Julia, you can use Unicode symbols, so you can actually use math operators. Like here I have nabla for the gradient and nabla dot for the divergence. So here's how your equation would look like in the code. Here's an example of a shallow water equation on a rotating sphere, where this is in vector invariant form. On the left, you see it on a regular grid. On the right, you see it on a curvilinear or orthogonal basis. So you have all of these covariant terms that pop up. In our code, this is how it looks like. So you have two equations. The first one is continuity of mass. And here's how it looks like. So you have dy dt, first equation is in h, which is divergence of h times u. So you can really read the code and it's like reading the math. And also the second equation here, dy dt equation for u, which is equal to everything on the right hand side. So we have negative gradient g times this term minus norm of u squared, and then the Coriolis term. So it's really user-friendly and intuitive. Some examples. These are typical examples in atmospheric science, typical test cases. So shallow water equation on the left with a mountain top. So here we have the atmosphere and the flow circulates around the mountain. So you can see that there is this mountain where we just circulate around. On the right panel, it's called a barotropic instability test, where we start with this perturbation and then it eventually evolves into an unstable vortices. Okay, so these are some of the test cases that we added. Something that I particularly paid some attention to and some work into is the stabilization of some advection problems. So advection, so pure transport problem here, just linear advection, where we have that little q denotes some tracer concentration. So it could be the mixing ratio or mass of dry air in this type of problems. And again, here we can see how simple the interface looks like. So the first equation is just negative divergence of rho times u. And again, in the code, we have negative divergence of rho times u. So it's very user-friendly. However, we know that if we use the spectral operator in the horizontal, the spectral advection operator is oscillatory. But due to its mimetic properties in this case, it is still locally conservative and it has a monotone property with respect to element averages, which means we conserve mass, or in this case, water concentration inside the element averages. To stabilize this problem, we use a class of what is called optimization-based, locally conservative quasi-monotone limiters, which are monotone with respect to a spectral element nodal values. These have been defined in this paper, GUBA 2014. They maintain quasi-monotonicity, and the only additional inter-element communication that you add, so the only additional cost, computational cost that you add is just to determine some suitable bounds. So here we see a typical example, P equals 6. So we have a 6-order discretization, 20 by 20 by 6 elements, effective resolution of 0.75 degrees at the equator. Is a typical example here that challenges your solver is the slotted cylinder case, because of the very sharp features here, you really challenge your solver. So on the left panel, we see no limiter, so no stabilization, and we can see how the solution quickly forms some undesired artifacts. So we see how this solution has these undesired artifacts. On the right panel, we see with the limiter stabilization. And you can see how smooth the same simulation looks. I also paid some attention to linear upwinding in 1D, so in the vertical direction. So remember, in the vertical direction in this package, we use staggered finite differences. However, to overcome some of the challenges, again, for pure advection, pure transport problem, we consider flux correlated transport. So this approximates the solution with a high order scheme in regions where the solution is smooth, and a low order monotone scheme in regions where the solution is poorly resolved or discontinuous. So for instance, here we see just the first order upwind on the left most panel. And I covered some of these properties today in class, so some of my students might recognize that this method is very dispersive. So it has a lateral shift of the wave. It is just a little bit distributive. That's not a problem. On the other hand, this problem here, which is third order upwind, it is less distributive and less dispersive, but it does exhibit these undesired overshoots and undershoots. So how do we fix that problem? With this scheme, which is called Zalesak flux correlated transport, which gets rid of entirely of the overshoots and undershoots, and it is not as dispersive. It is not as bad. Questions here? Okay. Now, very quickly to some of the final parts of this project that I worked on. Oops, my computer. Okay. I also worked on what is called the coupler. The coupler is another software package which is dedicated to coupling all of these different systems together. So as I said, historically, different components of climate models have been even developed by different teams in different institutions, maybe one in a national lab, one in another national lab. They might have used even a different language. They might have used totally different code infrastructure. In this case, we're using the coupler, everything in this, again, same language, so we don't have two language barriers. And for instance, let's say we want to couple the ocean model, which is developed by the MIT team, with the Atmos model, which is developed by the Caltech team. And we have to exchange quantities. We have to make sure that grids overlap, quantities are defined at the same grid points, and so on. So the coupler does not only exchange physical quantities when, for instance, in this example, you couple the ocean and the atmosphere, you have turbulent fluxes, you have precipitation, so stuff comes down from the atmosphere into the ocean. You have albedo, so the radiative energy fluxes, some of them are reflected, some of them are absorbed. You have all of these exchanges of quantity. You also have to be careful about the grid and the time stepping. So different models can use different grids. For instance, the ocean model uses the conformal cube sphere. Why? Because conformal cube sphere has orthogonal grid lines. They like to use this because they use finite volume formulation. So it is desirable to have orthogonal grid lines. However, in the atmosphere, we use spectral element method. In the horizontal, we do not care about orthogonal grid lines, because an element is defined on an element, does not need to know about the surrounding elements, could have totally different shape. So we use this one because it has a best CSL condition restriction. So when you couple two models who have different grids, you first have to regrid. That's what we say. Regrid is find the overlapping points. And also when you couple models in time, you have to be careful because there are different ways of coupling systems. This is a simple explicit coupling when you just run the two models in parallel. Let's say you run the ocean model with some initialization. You run the ocean and the atmosphere, and at given time steps that coincide for the two models, you see the quantities of interest, like energy fluxes. This is not the only way to do this. There are also leapfrog schemes and different types of schemes, but you have to be careful because your energy can grow unbounded. Yes. So in the coupler, also some of the work that we've done was to allow different hierarchies. So you can allow, for instance, different model hierarchy. So a simplest model is just in 1D, and then you can increase complexity by going in 2D and 3D. But also you can allow different physics. So that's a different hierarchy of complexity. This is just an example of, again, an atmospheric simulation up to 180 days of simulation. So this is a large global scale simulation up to 180 days of the temperature. So in the coupler, we have to be coupling different models with different complexity and different physics. So you keep adding complexity. So for instance, this is AMIP, that's what they call it in climate science. It stands for model intercomparison. These are the effective simulations that they care about when they meet, the policymakers meet, for instance, at COP meetings. They care about this type of comparison. So that's why they're called AMIP, Model Intercomparison Project. Okay, some very recent projects I've been working on with Dr. Castillo on transitioning the MOL library into an open source ecosystem. So what is from an open source product, the transition to an open source ecosystem? It involves trying to acquire external users and developers, trying to adhere to some best practices and standards, for instance, add documentation, tutorials, examples, unit testing, best engineering principles and best software design principles like continuous integration, test-driven design. So this is a project it's an ongoing project with Dr. Castillo's research group. And in the future, this is just my conclusion, we're gonna have some fun with we're working on potentially on some entropy stable methods for combustion applications. So thank you so much for your attention. I also want to point out that I do some mentoring, volunteering work, some mentoring and engagement. For instance, I've been a mentor at some camps for graduate students, especially in applied math and computational sciences. I'm always an advocate for invisible and visible disabilities in STEM, women in STEM, international students, upward mobility, systemic exclusion of underrepresented groups. I'm very active in industrial workshops, and if you have questions about industrial workshops, you can ask me. There is one workshop that is called MPI, Mathematical Problems in Industry. And also, I care a lot about student success and professional development, so I might share a lot of resources that might be useful to you. Thank you, guys.
Any questions?
For comment, there was a question about the performance of the Julia versus Fortran.
Yes.
So the Cologne group maintains both the Fluxo code, which is Fortran,
Yes.
and the Trixie code,
Yes.
which is Julia. When they compared those, the Julia code actually beats the Fortran code by a little bit. Now, there's a caveat. The Fortran code was older, and they did nothing to do any kind of optimization. The Julia code, if you write just a plain Julia code, it is going to be slow.
Yeah.
They worked real hard. They had to import a whole bunch of libraries. They can't even use the standard libraries for doing vector operations and the like. So you need to use that whole ecosystem in order to get the performance.
Yeah, so Julia has a duality. It can be very simple, user-friendly, and naive. But if you are naive as a programmer, it's going to be super slow. It's going to be probably as slow as MATLAB. However, if you want to be more like hardcore performance engineer, you can. So it really offers both. It is the promise to offer the best of both worlds. Yes.
Like I use Julia for some of the scripts for my research, and it is very nice because of that. And like even the data types are explicit, like C or Fortran.
Yes.
But there's like a data type hierarchy. So if you're newer, you could just put any as the data type, or you can go all the way to specifics like
yes,
int 32 or
yes,
like that.
yes. you can really be as specific as you want if you want your the compiler to be optimized to optimize for specific data types.
Any question from the back?
Also, you can do it as the artifact of product and so on, startup.
I'm sorry, I couldn't hear.
Also, you can do the artifact of guys. Also, do it as the artifact of guys.
Well, the first time it executes any function, it has the pre-compilation time.
Like that.
Yes, but that's usually not a burden for like this type of like large scale simulations. So that's the overhead is considered, is taken into account.
Any other question that has nothing to do with Julia?
But people are interested. It's a good sign. Okay. Well,
On that note, we want to thank our speaker one more time.